Welcome to the another segment of polymer process engineering. Here we are going to discuss the second part of the characteristics of polymers. You see, in the previous lecture we discussed different aspects pertaining to the characteristics of polymers, and most importantly we discussed about the molecular weight, which is very integral part of the characteristic determination, and then molecular weight distribution. In this particular segment we are going to discuss about the branching, cross-linking, flexibility, crystallinity and amorphous behavior of polymers, and then thermal transitions. So let's take the branching. The branching in the polymer, this cannot be easily determined as either molecular weight or the molecular weight distribution. So basically in different instances, the relative effect of branching or certain measurements, this can be indicated. Let us take example. Branching will generally depress the glass transition temperature of a polymer. Now, glass transition temperature is a very important thing where when upon heating the polymer starts the melt. That is the triggering point, and that depends on the molecular weight. So, if a polymer has not been affected by other possible glass transition depressant such as copolymer, additives or change in the morphology, the branching could have occurred. So, the degree of a branching is the effect of intrinsic viscosity. Now, the greater the branching, the more compact of the packing of the polymer in the solution. It is like this, that we are having the different chains, and if the branching is on, then the more compact structure would be there, and that results the equal molecular weights. A branch polymer will have a lower intrinsic viscosity. So, when we determine the molecular weight distribution through the viscometer, it plays a vital role. Now, let us take an example, like since the branched molecule, they tend to become still more highly branched, they concentrate at a high molecular weight and of distribution. So, the resulting presence of a long high molecular weight tail, this reflects the possibility of branching. This can increase the solubility of a polymer. Let us take up the cross-linking. Now, cross-linking is not an easily determined characteristics, because cross-linking moves a polymer towards insolubility or infusibility. So, because of the presence of a network structure. So, one possible indication of the cross-linking is a change of polymer's fusibility or solubility. Now, a change in a polymer property itself can indicate the cross-linking. So, another different methods are there for determination of the cross-linking. One method is to measure a property before and after addition of varying amount of chemical that will destroy the cross-linkage, so that they can break this network and then determine a relative change of property. This indicates the relative amount of cross-linking. Some of the spectrophotometric techniques are available to determine the cross-linking aspects. Now, here you see that different type of cross-linking affects the modulus temperature. Now, here the temperature versus the crystalline cross-linking, different type of effects is been discussed in this particular plot. The flexibility, the chain flexibility, this affects the ability of polymer to crystallize. The excessive flexibility in a polymer chain, as in the polysiloxanes and a natural rubber, this led to an inability of the chains to pack. The chain conformation, this may require the packing, which cannot be maintained because of the high flexibility of the chains. The most basic approach of measuring the polymer chain flexibility is to use the concept of completely flexible chain molecule. Then introduce the way in which the structure can restrict the rotation, hence alter flexibility. So, we are having the, say in a hypothetical way, you are having the complete flexible system, and then you restrict the flexibility, you restrict the motion of the chains, you restrict the rotation of the chains, and then alter the flexibility, and you measure all these things. Like polyacrylonitrile, which is theoretically 100% flexible, is actually stiff because of the steric hindrance of its large nitrile groups. So, steric hindrance causes the stiffness. Now polyamides, they are again theoretically 100% flexible, but they are quite stiff because of the hydrogen bonding between the chains. So all these things. So suppose if you wish to make them then 100% flexible, you need to destroy the hydrogen bonding or you need to eliminate the steric hindrance. The stiffness of the chain, this can be obtained by the value of r square, which is the mean square end-to-end distance of a chain. Now, this is by the angular light scattering of a dilute polymer solution or simultaneous stress, and then Befringement's measurement on a solid polymer on its rubbery stage. So, this is the mathematical representation for the measurement of stiffness. Now, here N is the number of links in the polymer chain and L naught is the length of each link. Another useful method for measuring the flexibility is to use the material's sonic modulus. The sample used, this should be unoriented, measured below the glass transition temperature. Now, if it is done, the chain stiffness will correlate with the sonic velocity, and that is the greater the velocity, the greater the chain stiffness. So, by this way you can find out the flexibility. Crystalline and amorphous behavior. The solid polymers, they differ from ordinary low molecular weight compound in the nature of their physical state or morphology. So, the most polymer, they show the simultaneous characteristics of both crystallinity and amorphous. X-ray or electron diffraction patterns, they often show the sharp feature typical of three-dimensional ordered crystalline solids as well as in the diffuse unordered features characteristics of amorphous solids. The term crystalline and amorphous, they are used to indicate the order and unordered polymer region respectively. The different polymers, they show the different degree of crystalline behavior, and the known polymer constitute a spectrum of material from those that are completely amorphous to other that possess the low to moderate high crystallinity. The fringe micelle theory, this was developed way back in 1930, considers the polymer to consist of a small sized order crystalline region. They are termed as crystallites. They are embedded in an unordered amorphous polymer matrix. So, the polymer molecules, they are considered to pass through several different crystalline regions, with the crystallites being formed when extended chain segments from different polymer chains are precisely aligned together and undergo crystallization. Now, each polymer chain, this can contribute ordered segment to several crystallites. The segment of the chain between the crystallite makes the unordered amorphous matrix. This particular aspect is presented over here. This is a schematic diagram of fringed micelle model of polymer amorphous crystalline structure. The folded chain lamella theory, this arose in way back in 1950 when the polymer single crystals in the form of thin platelets termed lamella. This measures about 10,000 angstrom to 100 angstrom. They were grown from the polymer solution. So, previously people have expected, but it was contrary, that X-ray diffraction pattern, this shows the polymer chain axis to be parallel to the smaller dimension of the platelet. Now, since the polymer molecules, they are much larger than the 100 angstrom, the polymer molecules, they are presumed to fold back like this and forth on themselves in the according manner like process of crystallization. The chain folding, this was unexpected since the most thermodynamically stable crystals in one involving completely extended chains. So, the kinetically it is difficult to achieve the chain folding, which is apparently the system's compromise for achieving a highly stable crystal structure under the normal crystallization condition. Sometimes the non-adjacent unitary or switchboard model molecule, they wander through the non-regular surface of a lamella before re-entering the lamella or a neighboring lamella, like here you see this particular aspect. In the chain folded lamella, the picture of polymer crystallinity is less than 100%, crystallinity is attributed to defects in the chain folding process. Now, this defect or their defects, this may be imperfect folds like this, irregularities in packing, chain entanglements, loose chain ends, dislocation, occult impurities, or numerous other imperfections. The adjacent re-entry, like here, and the switchboard model, they differ in detail of what constitutes the chain folding defects. The switchboard model, this usually indicates the most defects, they are in the crystal surfaces, while the adjacent re-entry model indicates the defects, these are located as much within the crystals as at the crystal surfaces. Melt crystallized polymers, they have the most prominent structural features of the polymer crystals. The chains are oriented particularly to the lamella face so that the chain folding must occur. Now, the chain folding usually is the maximum for the polymer crystals slowly near the crystalline melting temperature. So, the fast cooling, and sometimes it is referred as a quenching, this gives the more chaotic crystallization which less than the chain folding, and the melt crystallization often develops a spherical spherulitic growth which can be seen under the microscope or only in the microscope. Nucleation of the crystal growth, this occurs at various nuclei, and the crystal growth, this proceeds in the radical fashion from each nucleus until the growth front from the neighboring structure impinges on each other. Now, these spherical structures, sometimes termed spherulities, they completely fill the volume of crystallized polymer sample. Now, this spherulities, they have a different size, and degrees of perfection depend on the specific polymer and crystallization conditions. Spherulite, this is a complex polycrystalline structure. The nucleus of spherulitic growth is the single crystal, which a multi-layered stake is formed, and each lamella extends to form a lamellar fibril. The flat ribbon-like lamellae, like here you see, diverge, twist and branch as they grow outward from the nucleus. Now, the growth usually occurs by the chain folding with the polymer chain axis being perpendicular to the length of the lamella. Now, the strength of the polymer, this indicates that more than van der Waals forces holds lamella, and these are interlamellar or intercrystalline fibrils. They are also termed as the tie molecules between the lamellar fibrils within the spherulity and between the fibrils of different spherulities. Some of the polymer molecules, they simultaneously participate in the growth of two or more adjacent lamellae and provide molecular link that reinforce the crystalline structure. So, the chain axis of the tie molecule lie parallel to the long axis of the link. Each link between the lamellae is an extended chain type of a single crystal. The tie molecule are the main component of the modern picture of the polymer crystallinity, which is the carryover from the fringed micelle theory. The amorphous content of semicrystalline or melt crystallized polymer, this sample consists of the defects in the chain folding structure and the tie molecule and the material that either because of the entanglement like this are not included in the growing lamellar fibrils or is rejected from it owing to its unacceptable nature. Some natural polymers like cotton, silk, cellulose, they have the extended chain morphology, but their morphologies are determined by enzymatically controlled synthesis and crystallization processes. The extended chain morphology is obtained in some of the synthetic polymers under the certain circumstances. So, this includes the crystallization from the melt under pressure or applied stress crystallization of the polymer from the liquid crystalline state. A variety of the technique has been used to determine the extent of crystallinity in the polymer. This includes XRD or X-ray diffraction, density, infrared NMR, and a heat of fusion. The XRD is the most direct method, but it requires somewhat different separation of the crystalline and amorphous scattering envelopes. The other method are used, which are indirect methods, but easier to use since one need not to be an expert in XRD tool. Heat of fusion is probably the most often used method since reliable thermal analysis instruments are commercially available and easy to use. The difficulty in using the thermal analysis like DSC or differential scanning calorimetry or DTA, differential thermal analysis, or any other indirect method is uncertainty in the values of the quantity measured for 0 to 100% crystalline sample, since such samples seldom exist. So, very rare or to find out such kind of a reference sample. The best technique is to calibrate the method with the sample those crystallinity has been determined by XRD. Now, how we can determine the polymer crystallinity? This is regardless of the precise picture of order and disorder in polymer. The prime consideration that should be emphasized is that the polymer have a tendency to crystallize. The extent of this crystallization tendency plays a most significant role in the practical way in which the polymer are used. The consequence of the large effect of crystallinity on thermal, mechanical and other important properties of the polymer. The different polymer, they have been different properties, they are synthesized and used differently because of the varying degree of crystallinity and thereby varying degree of the processes. The extent of crystallinity, this developed in a polymer sample, is a consequence of both thermodynamic and kinetic factor. So, we will notice that the general tendency of crystallize under the moderate crystallization condition, that is the condition that exclude the extremes of time, temperature and pressure. These three are the most important variables. Thermodynamically, crystallizable polymers, they generally most crystallize at reasonable rates, and if crystallinity is to be employed from a practical viewpoint. Now, the extent to which a polymer crystallizes, this depends on whether its structure is conducive to packing into the crystalline state and on the magnitude of the secondary attractive forces of the polymer chains. Now, packing is facilitated for polymer chain that have structural regularities, compactness, streamlining and some degree of flexibility. The stronger the secondary attractive forces, the greater will be the driving force for the ordering and crystallization of polymer chains. Now, some polymers, they are highly crystalline primarily because their structure is conducive to packing, and still some polymers and other polymers, both factors may be favorable for the crystallization. Polyethylene, let us take the example of polyethylene. It is essentially the best structure in terms of its ability to pack into the crystalline state. It's very simple and perfectly regular structure allows chain to pack tightly and without any restriction as to which the segment of one chain need line up next to which other segment of the same chain of another chain. The flexibility of the polyethylene chain is also very conducive. This is conducive towards the crystallization in the conformation which may require for the packing. This can be easily achieved even though the secondary attractive force, they are small, as forces are smaller. Polyethylene crystallizes easily and to a high degree because of its simple and regular structure, the linear structure. The polymer other than the polyethylene have the less simple and regular chains. Polycaprolactam, this can be considered as a modified polyethylene, which the chain can contain the amide group between every 5 methylene. And polycaprolactam and other polyamides are highly crystalline polymers. Since the amide group is a polar one and leads to much larger secondary attractive force in polyamide. This is due to the hydrogen bonding. The polyamide chains, they are not simple for those polyethylene, and packing requires that the chain segments be brought together so that the amide groups are aligned. This restriction leads to somewhat lesser degree of crystallization in the polyamides than expected, and that is based only on a consideration of high secondary attractive forces. Now, the crystallinity in the polymer, like polyamide, this can be significantly increased by mechanically stretching it to facilitate the ordering and alignment of polymer chain. So, the polymers such as polystyrene, PVC, polymethyl methacrylate, PMMA, they show very poor crystallization tendency. So, the loss of structural simplicity, this compared to the polyethylene, results in a marked decrease in the tendency toward crystallization. Fluorocarbon polymers such as PVF, polyvinyl fluoride, or polyvinylidene fluoride, or polytetrafluoroethylene, they are exceptions. These polymers show considerable crystallinity since the small size of fluorine does not prelude packing into the crystalline state or crystalline lattice. The crystallization is also aided by the high degree of attractive forces, high secondary attractive forces, coupled with symmetry account of presence of significant crystallinity in polyvinyl leadine chloride. Symmetry alone with the significant polarity as in the polyisobutylene is insufficient for the development of crystallinity. The polymers with rigid cyclic structure in the polymer chain, as in the cellulose or a polyethylene terephthalate, they are difficult to crystallize. Moderate crystallization does occur in these cases, and as a result of their polar polymer chains. The biosynthesis of cotton proceeds with an enzymatic ordering of the polymer chain in spite of the rigid polymer chains. So, excess chain rigidity in the polymer, this is due to the extensive cross-linking, because the cross-linking always hinders the free movement of the chains. Now, this can be reflected in the phenol formaldehyde and a urea formaldehyde polymer, and this completely prevents the crystallization. Now, sometimes the excess chain rigidity is causes several processability problems, which can be reduced by application during application of various additives during the course of processing. Let us talk about the thermal transitions. The polymeric materials, they are characterized by two major type of transition temperatures: the crystalline melting temperature Tm and the glass transition temperature, that is Tg. The crystalline melting temperature is the melting temperature of the crystalline domains of a polymer sample. This is the basic definition of Tm. The glass transition temperature is the temperature at which the amorphous domain of a polymer take on the characteristic properties of the glassy state: brittleness, stiffness, and rigidity. The difference between the two thermal transition, this can be explained more clearly by considering the changes that occur in the liquid polymer as it is cooled. So, you heat a liquid polymer, polyethylene, and then you observe the behavior during the cooling. The translational, rotational, vibrational energies of the polymer molecule decrease on cooling when the total energies of the molecule have fallen to the point where the translational and rotational energies are essentially zero. The crystallization is possible. If certain symmetry requirement they are met, the molecule are able to pack into ordered lattice arrangement and the crystallization occurs. However, not all polymers meet the necessary symmetry requirement for the crystallization. Now, if symmetry requirement are not met, the crystallization does not take place, but energies of the molecules continue to decrease as the temperature decreases. A temperature finally reached at glass transition temperature at which the long range motion of the polymer chain stops or ceased. The long range motion, they are also referred as a segmental motion. This refers to the motion of a segment of the polymer chain by concerted rotation of bond and end of the segment. Whether a polymer sample exhibits both thermal transition or only one depends on its morphology. Now, if it is a completely amorphous polymer, it shows only Tg, that is the glass transition temperature, and a completely crystalline polymer show the Tm. So, semi-crystalline polymer exhibit both the crystallinity melting and a glass transition temperature, so it is in between. Now, this particular figure shows the changes in the specific volume with respect to the temperature of completely amorphous and a completely crystalline polymers with respect to the temperature and specific volume. You see that here the structure, the movement of amorphous, and this is the semi-crystalline, and beyond this, this is the crystalline one. Now, Tm is the first order transition with a discontinuous change in the specific volume at the transition temperature, and a glass transition temperature is a second order transition involving only a change in the temperature coefficient of a specific volume. So, a plot of temperature coefficient of a specific volume versus temperature, this shows the discontinuity. So, if you plot, then you will observe that this continuity is there. The corresponding plot for the semi-crystalline polymer consists of a plot of a crystalline polymer plus a dotted portion of glass transition. Here you see. A variety of methods have been used to determine the glass transition temperature and Tm. This includes the dilatometry, that is the determination of specific volume, thermal analysis, dynamic mechanical behavior, dielectric loss, broadline NMR, etc. And the most common method is the DSC, that is the differential scanning calorimetry. This reflects the change in the heat capacity of a sample as a function of temperature by measuring the heat flow required to maintain the zero temperature differential between an inert reference material and a polymeric material. The melting of a polymer takes place over a wider temperature range than that observed for a small organic molecule such as benzoic acid, and due to the presence of a different size crystalline region and more complicated process for melting of a large molecules. Glass transition temperature also occurs over a wide temperature range and determined by extrapolation of two linear regions before and after glass transition. So, the glass transition is a less well understood process than melting. Now, there are various indications that it is the least partially a kinetic phenomena, and experimentally determined values of glass transition temperatures vary significantly with the time scale of measurement. Now, faster cooling results the higher glass transition values. Now, significant densification still takes place below the glass transition temperature, where the amount of dependent on the cooling rate. So, the best visualization of glass transition involves the existence of a modest range of temperature at which there is a cessation of the segmental motions of different polymeric chains. Now, some polymers may undergo the thermal transition in addition to glass transition and Tm, and this includes the crystal-crystal transitions. The values of glass transition and temperature and TEM for polymer affects the mechanical properties at any particular temperature and determine the temperature range in which the polymer can be employed. Let us consider the manner in which the Tg and Tm vary from one polymer to another. One can discuss the two transitions simultaneously since both are affected similarly by consideration of polymer structures. So, the polymers, those who are having the low glass transition values usually have the low Tm values, high Tg and high Tm values are usually found together. Now, the polymer chains that do not easily undergo the bond rotation so as to pass through a glass transition would also be expected to melt with the difficulty. The high secondary attractive forces also decreases the mobility of the amorphous polymer chain. So, the movement of the chain is very important. Decreased mobility of the polymer chain increase the chain rigidity more compact structure, high glass transition temperature, and the TM value of the crystalline polymer they produced from such rigid chains would also be very high. The effect of substituents are not always easy to understand. Usually the comparison of polypropylene, polyvinyl chloride, polyvinyl fluoride, polyisobutylene, polyvinylidene chloride and polyvinylidene fluoride. They are respectively, this shows the polymers from 1:1 distribution of ethylene. They have the lower Tg and Tm values. Then do those from the mono distributed or mono substituted ethylenes. Apparently, the presence of two side groups instead of one, this separates the polymer chain from each other and results in more flexible polymer chain. Therefore, the effect of substituents on the glass transition temperature and TM depends on the number and identity. The rigidity of the polymer chain is especially high when they are cyclic structure in the main polymer chains. Although the glass transition and TM depends similarly on the molecular structure, the variation in the two transition temperature do not always quantitative parallel each other. The TM values which can be seen to generally increase in some same order, but there are many polymers whose TM values do not follow in the same extent order. Therefore, the polyethylene and polyoxymethylene, they have the low glass transition values because of their high flexible chains. However, their simple and regular structure yield tightly packed crystal structure with high TM values. So, an empirical consideration of the ratio of glass transition versus TM, that is called the Kelvin temperature sometimes, the various polymers at this particular aspect. So, when the Tg equal to Tm ratio approximately half of the symmetric polymers. Now, it should be evident that some of the factors that decrease the crystallization tendency of a polymer also led to increased value of Tm, and because Tm is also, if Tm is increasing, then Tg will also increase. So, the reason for this is that the extent of crystallinity developed in polymer is both kinetically, thermodynamically controlled, while the melting temperature is only thermodynamically controlled. The comparative differences between the polyethylene and polyhexamethylene adipamide, this polyethylene tends to crystallize easier and faster than the polyamide because of its simple and highly regular structure and usually obtained with the greater degree of crystallinity. On the other hand, if we talk about the Tm for the polyamide, which is much higher, say by 130 degrees Celsius, than that of the polyethylene because of the much greater secondary forces. So, dear friends, in this particular segment, we discussed about the different behaviors of the polymers, especially the glass transition temperature and melting temperature, and we discussed about the different aspects through which we can determine the properties. For your convenience, we included couple of references. You can utilize those references as and when needed. Thank you very much.